have to from this solution, from this you have to add an extra term here. But the main scheme is like this. It's working like this. Okay? So now the last point or the last details is that this gradient-based method works well. You have still probably adapt this alpha, and but still this may not convert. This may oscillate. So I mean that depending for the quadratic criterion is okay. In general, it is not any problem. But if you had something which is not quadratic, so it means that the shape of the criterion may not be a quadratic, a convex situation. So in those cases, it may happen that, for example, if you have, let me find a sheet of the paper. Do you have just one foil? Yeah. Yes. Okay. Thank you. If F, which is here a huge dimensional matrix, if F had only two components, 2 pixels. So here is let F1 and here is F2. If the criterion has really a 1 minima, would be the situation like this. So it is very easy, and all these algorithms arrive very fast to this optimum. But if the situation is something like this, so it means that if you start by here, you arrive here, you arrive here, you arrive here, you arrive here, and if the minimum is somewhere here, you may oscillate a lot. So let me show this differently. If you had only two values, F1 and F2, and the criterion was likely, if the criterion is something like this is easy. So it shows these are the ISO criteria. Okay, so you have this, and you look the values of ISO criteria. So this is easy case. But if you had the situation like if you have a situation like this, so assume that the optimum is here, so they are not the circles, they are like this. So if you start, for example, from here, you may go oscillating like this, like this, like this, like this. And this will not, this takes a long time to arrive at the final solution. So in those cases, it is better to change here and do not put here the gradient and put another direction and combine in such a way that if you are here and you arrive here, if you continue in the same way in the direction of the gradient, you arrive here, you arrive here, you arrive here, and so on. What would be the best to do is that if in the first step I go here, in the next step, in place of going in the direction of the gradient, you may go at a direction which is perpendicular to this. You may arrive here, and then perpendicular to this, and so on. So it means that you need to compute the directions in such a way that 2 consecutive directions be perpendicular. And this brings us to the conjugate gradient techniques. I'm not going to discuss more in details of these optimization techniques because there are too much to say. Really, there are too much to say about the optimization techniques. But just the main idea of the conjugate gradient techniques is that in place of the gradient, you put a direction, and you do in such a way that two consecutive directions be perpendicular. So it means that the equations is not just this. The equations means you have to add another equations, d as a function, dk plus 1 as a function of dk minus 1. And another equation which, so in place of having only one equation, you may have 2 or 3 equations to implement. So implementation of these algorithms is a little more tricky, and there exist many optimization algorithms that you can use. This scheme that I have given you, actually, if you, for any inverse problem, this will work for any inverse problem actually. And so when you are faced to an inverse problem, no matter if it is a convolution, if it is a two-dimensional convolution, if it is a Radon transform, if it is any other transformation, if you are able to solve the forward problem with best cost as you want. If it is a convolution, the convolution you will do it by FFT, for example. You gain cost. So if you are able to give a program in which you put the f at the input and you obtain g at the output, so it means computing the forward problem, you need a program which is forward, which gives as input f and gives at output g. For example, in the case of convolution, you need what? You need to know impulse response, and what I proposed in the exercise to do, design a program which may call, I propose you to use direct. In French, I have used that direct. So you can use some of my programs if you want. Direct, you give it f as the input, impulse response, and the method, the number of the method. So you may do this computation, you may make this forward computation with different method and compare the performances, for example. So you have a forward method, a direct method, and you need to do an adjoint operator. I call it transp, just because that was transposition of the matrix. And what is the input of this transp is G, and the output is something which is delta F, okay? Or you can just call it F, it doesn't matter. And what you need, for example, in the case of convolution, again you need H, and you need, say, a number of the method. And if you have these two programs written, then writing this is very easy. It's just one line of MATLAB. This is direct, this is the difference, and this is adjoint. And these are very, in general, not very costly to implement also. You have to be, we took the case where this term was easy. But if you add, for example, if you add a D here, what would be the difference? Here you will have D transpose DF. Here you will have D transpose D. Here you will have D transpose D. So here you will have d transpose d. But still this term is not too costly because d is the operator of derivation. And df is just compute the derivative of the signal. And computing the derivative is just the difference between two successive samples. So it is not costly. And d transpose again is another derivation. So still all this part stays reasonable at the cost of the computation. In the case of derivation, you can do it by convolution, because the operation of the derivation is just a convolution again. Convolution with something which is 1 and minus 1. So these are some of the details that you may know. And so this is the way that I propose you to do the computation. Let me to go a little more specific. Other priors that the quadratic energy or smoothness. So other priors or other regularization terms. Here I like to do this like this, omega to f, and omega to f, which is so we are talking about different regularization operators. The first operator that we took about was this. And this is just sum of fj power 2. The second expression that we gave was smoothness. This is energy. This is smoothness, which is sum over G. The operation of df is just fj minus 1 over 2. D is the operator of derivative. And the matrix D here actually is a matrix which is like this. 1 here, minus 1, 1, and again minus 1, 1, goes up to 1, minus 1, here 0, and here 0. This operator is operator of derivation. Why? Because applying D on F, F1, F2, Fn, in the first value is F1, second value is F2 minus F1, third value is F3 minus F2. This is exactly the derivation, no? Or a good approximation of the derivation. So D multiplied by F power 2 can be shown that it is like this. This is the computation that you have to do. Smoothness. And now you can add any other. I say that sometimes the people call this as to be quadratic regularization of order 0. This as the quadratic regularization of order 1. because this is derivative of order 1. This is derivative of order 0, no derivative. And you can add derivative of order 2 and so on and so on. Okay, so you can put any other derivative operator. For example, a derivative operator order 2 would be something like this. 1 here, minus 1 here, and then minus 1, 2, minus 1. Here. In the center you have 2, minus 1 or something like that. Yeah, minus 1. And this goes up to this. Is second order derivative. Something like that. Don't go into details here. This is not so important. And finally, sometimes you may have other prior information. For example, you would like to impose something which is, you know that Fj must be absolutely positive. Before talking about the positivity, I talk about another measure which is like this. Omega f is sum over j of Fj in absolute value. Here was absolute value power 2. Here is just absolute value. We say this is a L2 regularization. This is a L1 regularization. You can do the same here. You have a smoothness L2, or you can also have the same thing but EC power 1. Or in more general, you can put power beta, EC L beta, and beta choose between 1 and 2. We can talk about generalized energy, or we can talk about generalized smoothness. And some more general cases would be to choose omega of f to be sum over g of a function, any robust function that you can choose of fj minus 1. And what are the different possibilities for phi of t or phi of z or no matter? You have t power 2. You have absolute value of t. You may have a function which is a combination of these two. Could be. Let me just show them phi of t as a function of t. T is the difference, huh? This is t. So you can have a quadratic. This is. You can have a linear. This is. You can have a combination of linear and quadratic. You can have, for example, quadratic up to here, and then linear. This is called Huber function. And you can have many other, and there has been a lot of papers, really a great number of papers, to propose different phi functions, regularization functions. And for each of them there are arguments. How y quadratic, y L1, y L2 L1, y even the all these functions that I have drawn up to now are convex functions. So for all these functions that I have drawn up to now, this function is convex. You know what is a convex function? Okay. But there are also some of the people have proposed non-convex functions for some reasons that I will explain a little later. For example, functions like this, quadratic up to a level, truncated quadratic, here like this. One of my oldest PhD students worked on this truncated quadratic regularization, and I will explain a little later why. And there has been many other functions like this truncated quadratic has a drawback, which has discontinuity, and discontinuity is not a good idea when you want to use gradient algorithm. So there has been people who propose like this. This is the inverse Lorentzian, and there has been really a great number of the propositions in the literature. You can find probably 1,000 papers, each one proposing one of these functions and describing why they have chosen this function, and so on and so on. There are a lot of papers on that. In particular in the 80s to 2000s, there has been a great number of the papers, scientific papers in regularization theory and inverse problems, who proposed the different 5 functions as the regularizer and discussed the details of that. Just to give you a very high level idea of why the people has proposed different solutions. Okay? To be able to discuss about this, to finish this today, so we are talking about choosing different choices of regularization function. We are talking about omega to f, which is the regularization part, and omega to f which is sum over j of phi of fj minus fj minus 1. And we are talking about the function phi of t. This is t, which means, let me not put t, but to delta f. It is more discussion, more appropriate. Delta fg. What are the different? Why there has been different solution proposed? If I consider, for example, let's come back to the deconvolution problem, and assume that your input signal would be something like that. This is the input signal, okay? And the output signal would be